Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone. We have been discussing MOSFET. So in the we have been discussing MOSFET. Let's recapitulate whatever we have discussed in the last class. We have come across the current voltage equation of the MOSFET, which was so this was the current voltage equation at triode region or nonlinear region. Okay, and triode region or non-saturation region, and IDS equal to Kn VGS minus VTH whole square. This is was in saturation region, right? So this was the current voltage equation we discussed in the last class, where Kn is known as transconduction parameter. Is equal to W by L, W by 2L, mu n Cox. Okay, so mu is the mobility of the carrier. In case of n-channel MOSFET, it is the mobility of electron. Although mobility of electron in the channel is much less than mobility of the electron in the bulk silicon. Okay, mobility of electron in the bulk silicon around 1300 or 1350, but in the channel it may be 500, 600 max. Okay. So mobility of the electron or mobility of the hole depending on the channel of the MOSFET. Cox is the oxide capacitance per unit area, and W is the width of the MOSFET, and L is the effective channel length. Okay, you will find another parameter in the book, particularly in Niemann's book. This is, they have written as Kn-2 W by L, where small Kn dash is equal to mu n Cox. Okay, this is different way, just the way of representing things. So anyway, so these are the two equations we have come across in the last class. So if I draw the output, if I draw the MOSFET characteristics, that is IDS versus VDS. You remember we plot for different values of VGS. Okay. So VGS, so different values of VGS, and we mentioned this is cutoff, and this is saturation, non-saturation, sorry, or triode region, and this is the saturation region. Okay, now here we so this is VDS sat, which is VGS minus VTH. Okay, lot of you have queries regarding why why even after pinch off even if we increase VDS, the IDS remains the same. Okay, that was many of you asked the same question in the last class. So this is the pinch off point, that is at that voltage. If we have channel is start decreasing from that particular VDS. Okay, and you know that you need additional VDS if you have more VGS, right? Because VDS sat is VGS minus VTH. You remember, for having the channel, this gate drain voltage should be good. So here we have VG and here is VS, and here is VD. So VG minus VS should be greater than VTH. This is also true. VG minus VD should be greater than VTH. This. So all along the channel, this relation needs to be maintained. So that channel is formed, right? I think this is clear from the last class discussion. Now you had a queries like why this current is not increasing even if we are increasing this drain source voltage. So even if we are increasing VD, why the current is fixed after pinch off? So if you I mentioned that I will clarify this point in the next class. So you see beyond pinch off. So say this is the so beyond pinch off, the channel is moving towards source, okay, and this particular position where there is basically no channel. So this is my drain and this is my source, okay, and this particular portion there is no channel for a particular VDS. Now what happens? The current so here the way it flows, the electrons will be basically dragged by this electric field, okay, which is drop across this depletion region. It is something like how to explain this? So this is my depletion region. You see in the you see this is reverse bias diode, right? This is a reverse bias PN junction. Now in reverse bias PN junction, okay, with increasing voltage, current doesn't increase, right? So current will increase up to when it reaches the pinch off, okay. So this is my, so it is like a reverse bias diode in this particular depletion region. In this particular depletion region, this is like a PN junction diode in reverse bias, and in reverse bias current doesn't increase. This is also true in case of BJT. You remember, in case of BJT, if this is a collector base collector junction, whatever current increase, current is coming from the emitter current, and once the carrier reaches here, the purpose of this depletion region is drag those carriers to collector. Okay, so in this point current is not increasing. Whatever current has, it is because of the carrier or because of the IE which is reaching at this depletion region. So this is also true here. This is also a reverse bias region, okay, and in the reverse bias region the current will basically increase when the channel is between drain and source, okay. So the channel is continuous between drain and source. So then the current will gradually increase. Now once the pinch off will occur, there is no channel between close to the drain, okay. So this region is basically reverse bias region, and in the purpose of this electric field present here, just to drag those electrons or collect those electrons to the drain, right? So the current will doesn't increase because it is a reverse bias. You remember the diode characteristics also. In diode characteristic, reverse bias current doesn't increase with voltage, okay. If you have extra current, say in case of BJT, or if you have like if you increase the temperature, there is additional carriers, so you have larger amount of current, but that larger amount of current remains fixed and it doesn't depends on diode reverse bias voltage. So this is also true here. Here also this is a reverse bias, drain and substrate is in reverse bias, okay, and whatever the electron or holes they will find here, the purpose of this electric field or this reverse bias is to drag those carriers to the drain. So the current doesn't increase once it reaches the pinch off. So before pinch off, the current will gradually increase, okay. It remains linear for very little VDS, but with increase in VDS, the current, there is a roll off because the channel width near the drain will decrease, okay. But once the pinch off will occur, the channel moves away from the drain, and so that reverse bias will not so current doesn't increase beyond that point because of that reverse bias in that drain substrate portion, okay. I hope this is clear now. So it's same like diode in the reverse bias or BJT base collector junction, okay. So we have discussed the IV characteristics and the current voltage relation of the MOSFET. Okay, couple of point I would like to discuss before we move to DC analysis of the MOSFET device, like we discussed the BJT DC analysis part. So in this case, what I want to cover a couple of points. One is like although we are saying the current IDS is independent of VDS, okay, that is not exactly true, and the current is little bit tilted with VDS, okay. Again, same like what we discuss in BJT, current is little bit tilted, it is not exactly independent of VDS, and that is because in the current voltage relation, that W by 2L, this L is L effective, okay, and as you are increasing your VDS, the effective gate length decreases because of the pinch off. So that is one thing I would like to discuss. There are other things I would like to mention. For example, if you have higher doping concentration at substrate, okay, your VTH will increase. This is again obvious because you need to apply larger gate source voltage or larger voltage at the gate to invert the substrate. Okay, so if I have a substrate which is like P type, okay, so I have a P type substrate, maybe in the carrier concentration 10 to the power 16, and I have a P type substrate carrier concentration 10 to the power 17. This if you realize a n channel MOSFET here, this MOSFET will have higher VTH, okay, compared to the MOSFET with a lower substrate doping. Okay, so that is another point I would like to mention. Now, so far whatever we have discussed in the MOSFET, this is known as enhancement type MOSFET. Enhancement type MOSFET. Okay, there is additional MOSFET which is known as depletion type. What is depletion type MOSFET? In case of depletion, so depletion type MOSFET can also be P type or N type. Okay, in case of depletion type MOSFET, channel exists even so say I'm talking about N type MOSFET, P type, this is both N and P type, but say in case of N channel depletion type MOSFET, okay, channel exists even what I mean is purposefully we dope the channel region. Okay, purposefully we dope the channel region so that the channel remains there. So at VGS equal to 0 volt, okay, there will be channel. So channel is already there. You fabricate the device in such a way the channel is already there underneath the gate the oxide. Okay, gate silicon interface, there is channel already there. Channel is existing, and you need to deplete the channel. So in this particular type of N channel MOSFET, your threshold voltage, so channel is already there even if VGS equal to 0 volt. Okay, so what you have to do, you have to apply VGS negative voltage to remove the channel. Okay, so in other words VTH is negative for N channel MOSFET. Okay, usually VTH is positive. Okay, but in this case, as there is channel already there, you have fabricated the MOSFET in such a way channel is already there. So you need to apply negative voltage at the gate to remove the channel. Okay, so maybe the threshold voltage is -1 volt. So you have to apply below -1 volt, so -1.1, -1.5, etc. to remove the channel. Okay, so once it is over -1 volt, okay, so 0.9, 0.8 and so on, then the channel is there, okay, and it will act as a MOSFET. So this type of MOSFET is known as depletion type MOSFET, because you have to apply a voltage at the gate to deplete or remove the channel. Okay. Right. What else? Is there anything I am missing? Okay. Last thing I would like to mention is it is possible to have in nowadays CMOS is extremely important. CMOS is known as complementary MOS, that is complementary metal oxide semiconductor. Okay, what is CMOS? CMOS is both PMOS and NMOS. Okay, what is CMOS? CMOS is both, you have NMOS and PMOS. Okay, now this complementary MOS, so in earlier days we have only silicon wafer where we have only NMOS or only PMOS, but nowadays in the same silicon substrate we can fabricate both NMOS and PMOS together. So complementary because both NMOS and PMOS are present. How can we, what will be the structure of such a if we want to realize both NMOS and PMOS? In that case, maybe say we start with a p-type substrate. So if I have a p-type substrate, then what we can straight away do, we can straight away form n-channel MOSFET. Okay, now that n-channel MOSFET, okay, now what we in this n-channel MOSFET, if I on the same substrate I want to also realize p-channel MOSFET, because I said like in the complementary MOS or CMOS, okay, popularly known as CMOS, both NMOS and PMOS will be present in the same silicon substrate. This has huge importance. In your analog circuit class you will learn why NMOS is why CMOS is important, and you will see most of the circuit nowadays are made of CMOS. Okay, now in this case what we do, we realize a thing known as N-well. Okay, N-well, and in that N-well we then realize source and drain and gate of PMOS and NMOS. Okay, so here we realize PMOS in the N-well, and in the p-type substrate we realize NMOS. Okay, so what is N-well? In N-well, this we intentionally dope some part of the p-type substrate region to make it n-type. Okay, so this N-well has a doping concentration little bit higher than that of p-type substrate. Okay, so doping concentration is little bit higher than that of p-type substrate. So you see here the threshold voltage will be magnitude of the threshold voltage will be different, because this n-channel MOSFET is directly on the p-type substrate, whereas this p-channel MOSFET is in the another substrate, I mean the same substrate but within N-well, because we need n-type region to realize p-type MOS. Okay, and this N-well region will have little bit higher doping concentration than p-type substrate, so its threshold voltage will be little bit higher magnitude, but there are ways to control threshold voltage. Okay, that we are not going to discuss here, but what I want to say that nowadays in fact last 40 years, more than 40 years or so, close to 50 years, we have this kind of complementary MOS, where both NMOS and PMOS can be realized on the same silicon substrate. The only thing is we have to have a N well here. If we start our starting substrate is N-type substrate, okay, in that case on that substrate we will realize the PMOS directly, but for NMOS we have to have a P well. Okay, so depending on which substrate is the starting point, we have that complementary of that well, and we then realize the corresponding complementary MOS, right? And as I said, like we although this IDS VDS curve is not flat, and so there will be a slope, finite slope and finite output resistance, which we also have seen in case of BJT, and this output resistance can be calculated, okay, in the same way we did in case of BJT. Here VGS is constant, and this will be equal to 1 by lambda IDQ. Okay, IDQ is the Q point drain current, or IDSQ, and lambda is basically channel length modulation. So this is nothing but ID. This we'll discuss later on when we will go through the small signal model, but for the time being this is basically the early voltage divided by IDQ, okay, the output resistance. Now so let's now start the DC analysis part of MOSFET. DC analysis again very important to design the MOSFET circuit, because such DC analysis will then will be useful when we will discuss MOSFET as an amplifier. Okay. Now this DC analysis will mainly cover common source circuit, okay, like in the BJT we have covered common emitter circuit. So here we will cover common source circuit, okay. Typical common source circuit is like this. Here we have this is the supply voltage, okay. One resistor connected to drain is RD, okay. Source I have grounded, so source is in between gate and output. Usually we take output from here, okay, and this can be your input that we will basically discuss in the amplifier section later on, okay. Let's not bother about this part. So this is a typical common source circuit where the source is be grounded or in between input and output, okay. So source is common. Now this is a typical circuit of MOSFET, where we try to bias MOSFET in the saturation region, okay. You remember in case of BJT also we had similar circuit, but in case of BJT what we have assumed that the current here is current in the base is much less than that of say I2, okay. And you remember we straight away calculate the voltage here, which is basically the base emitter voltage, and that we wrote VCC R1 over R1 plus R2 multiplied by R2. This was true if we consider I2 much greater than IB, and if this is not true, then we have assumed that this is the calculated this in terms of V Thevenin and R Thevenin, you remember? Okay, but in this particular case, we don't have any gate current. Okay, we don't have any gate current. So so you see, we can straight away write the voltage here, which is basically Vg, say. Okay, so Vg, in this case Vg is equal to Vgs, because you see source is grounded, so voltage here is basically gate source voltage, that is Vgs, right? So Vgs equal to Vdd divided by R1 plus R2 multiplied by R2. Okay, so that's basically your Vgs. Now and what about your Vds? Vds is basically V out. Okay, that Vdd minus Ids Rd. So these are the equations. Okay, we basically will assume that Ids is equal to Kn Vgs minus Vth whole square. That is, we will assume that transistor is in the saturation region. Of course, we need to verify that. So we will assume Vds is greater than Vds sat in this particular case. If this condition is not valid, then we have to consider the equation of drain current in the triode region, right? So this is the typical circuit diagram for the DC analysis, and this is the typical biasing circuit in case of MOSFET. I am going little bit fast because we have discussed similar kind of things in case of BJT, so I thought that I can go a little bit faster here. Okay, now the thing is, in the same fashion as we did in case of BJT, we can add a resistor here. Okay, we can add a resistor in the from source, like we did in case of a emitter degeneration, you remember. So we can modify that circuit, and can add one additional resistor here. Again, this resistor acts as a negative feedback and helps in stabilizing the bias. Okay, this resistor acts as a negative feedback because now Vg is no longer equal to Vgs. So Vg will be equal to Vdd over R1 plus R2 multiplied by R2, but this is no longer, so this is your Vgs, right? So this equal to Vgs plus Ids multiplied by Re. Okay, right? So this Vgs Vg will be equal to Vgs plus Id multiplied by Re. So you see, for some reason, if there is any increase in Vg, okay, or decrease in Vg, because might be the resistor's value is not correct or so on, then that will be taken care of by this resistor Re. So it acts as a negative feedback. But like in the BJT also, we will see that this Re will reduce the gain. Okay, this Re will, when we will discuss the amplifier part, we will see that this Re will reduce the gain. Now if this Re will reduce the gain, in that case what we usually do, we apply a, you remember, we apply a capacitor here. Okay, to bypass this resistor fully or partially, so that the DC only see this resistor, but AC signal will not see this resistor. AC signal will see the short, will see it short and pass through that capacitor. So that we will discuss when we will go through the amplifier part. But just to completion of the discussion, so we can use a resistor, but a partially or fully we will bypass it as far as the AC signal is concerned. Let's go through some of the other configurations. For example, we can have this particular configuration in in MOSFET where MOSFET gate and drain is shorted. Okay, so if you come across such a circuit, you remember a problem we discussed in the last class, but let me just reiterate those who didn't understand that problem. So if we short your gate and drain, in that case you see this is your VGS and this is your VDS. So you see in this particular configuration VDS and equal to VGS. So you see VDS here equal to VGS for all the time. Okay, so VDS, in other words, VDS is greater than VGS minus VTH. VDS is greater than VGS minus VTH. So as VDS is greater than VGS minus VTH, this transistor is always in saturation. Always in saturation. So if you come across in a problem of such a transistor, okay, then you can consider this as you remember you have to consider this as it is in saturation, because here VDS is always greater than VGS minus VTH, because VDS is equal to VGS here, because this drain and gate is shorted. Okay, right. What else? We can also have you will also probably come across this the above mentioned or the example I mentioned in the last slide with so this is another configuration I would like to discuss. Here you see the top MOSFET say ML and bottom MOSFET say MD, and I'm applying an input voltage Vi, okay, and this is your VDD. Okay, here you see ML will always be in saturation, as I discussed in the last slide, simply because this gate and drain is shorted. Okay, so ML always be in saturation, and this VMD it depends on the Vi and this V out. Okay, whether it will be in saturation or triode region or cutoff region, etc. Right? But this ML will be in saturation. Usually this kind of circuit is ML is known as load transistor. Okay, so it is like a resistor. ML is like a load transistor, load, and MD is usually known as driver transistor. Driver transistor. Okay. You will see that. MOSFET? Sorry?
It's transistor or MOSFET?
Yeah, but MOSFET is also transistor, metal oxide semiconductor field effect transistor. Okay. Yeah. MOSFET is also transistor. Yeah. So so this is usually known as load transistor because it is like a resistor, and this is the driver transistor. You will see this kind of configuration used in several examples in the Niemann's book to solve problems. Okay, now this again like in BJT, we can use MOSFET as an inverter, although I probably didn't mention explicitly BJT inverters, but I'm just mentioning here, say NMOS inverter. What is inverter? Inverter is basically a digital gate. If we get opportunity, we will discuss a bit of a digital gates at the end of this course. So the inverter is inverter symbol is something like this, where if say this is your Vi and this is your Vout. If Vi is high, okay, if Vi is high, then Vout will be low, and Vi is low, then Vout will be high. So it is basically inverting. Whatever is input at the input, output is opposite to that of input. High means this is just a notation, but high means higher voltage and low means lower voltage. Okay, What is high, low, etc. we will discuss when we will discuss the digital circuits, but for the sake of completeness of this discussion, what I am saying that one of the application of MOSFET or BJT is use it as a inverter, as an inverter, where if we apply higher input voltage, the output voltage will be low, and if we apply lower input voltage, output voltage will be high. What is the typical circuit diagram of a MOSFET inverter? The typical circuit diagram of a MOSFET inverter is like this. So RD, the reason we write RD because D is connected, because it is connected to drain, so we write RD, okay, and RE we write because it is connected. I think I made a mistake in the last thing. So instead of RE, I think it should be RS. But anyway, so don't worry about it. Okay. I think they have usually we write usually we write here we write usually RS because it is connected to source. But don't worry about that because that's the usual convention. Okay. Usual convention is the resistor. The way we name it is connected to the terminal. Okay, so this is a typical NMOS inverter. Okay, how the circuit works. So if Vi is low, that is Vi is less than, if Vi is less than such that it is less than threshold voltage. So Vi is basically VGS. You see Vi is basically VGS, gate source voltage. Okay, so Vi is equal to VGS. So if Vi is less than VTH, what will happen? MOS is off, right? There is no current flowing through the MOSFET. So if we measure a voltage here, V out, so V out will be equal to VDD, you see, right? Because there is no current flowing through the MOSFET, so there is no voltage drop across RD. So entire voltage, if I measure a voltage here, the entire voltage will be across the MOSFET. Okay, so it is like a switch. So entire voltage will be across the MOSFET. So that means if you see, if the input is low, output is high. Okay, what about the other way around? If the input is high, okay, say nearly equal to VDD, say, so in that case it will take the transistor. Okay, if the input is too high, it will take the transistor in the saturation, in the triode region. Okay, saturation is in case of BJT in the triode region. So there will be lot of voltage drop across RD. Okay, because the current is high. Okay, MOS is on. In fact, current is very large. So IDS RD is quite large, and so V out will be nearly equal to 0. Okay, because the entire voltage will be across RD. Okay, so this is the in that case, if the Vi is high, you see V out equal to low. So it is acting as an inverter. When the input is high, output is low, and when the input is low, and then output is high. Okay, so this is typical NMOS inverter. In fact, we can have other circuits also, other digital circuits also. For example, we can have NAND gate, NOR gate, and so on and so forth. For example, we can have NAND gate using multiple MOS. Okay, for example, this is I hope it will even if I don't discuss this, it is just you will be able to understand that this will act as a NOR gate, NMOS NOR gate. Okay, similarly you can have NAND gate where you have two MOSFETs on top of one another. Okay, and so on and so forth. So different MOSFETs MOSFETs we can use to realize different digital gates. Okay, now what we actually do by biasing a simple MOSFET to put the MOSFET in the to keep the MOSFET within this saturation region. Okay, so here also we will have a load line. Depending on biasing, we will have a fixed VGS Q. Okay, so depending on what is your biasing resistors, you will have a fixed VGS Q. Okay, and so say this is your VGS Q. Okay, so the corresponding IDS Q and VDS Q we can find out from this load line. Okay, so here again VDS will be 0 and here again IDS will be 0. Okay, so that way you can find 2 points by finding this, by writing the equation of the IDS. Okay, here it is up to you. You can consider the effect of RDS or without RDS. If there is no RDS, you can straight away write VDD equal to VDS Q plus IDS Q RD if there is no RS, and you can straight away draw that load line by considering in one case VDS is equal to 0 and another case IDS is equal to 0 and so on. Okay, so I'm just skipping through these parts because these just very fresh. We have just discussed few class ago, and I don't want to keep on discussing it in a lengthy fashion because these are known. Okay, so what we do, we will keep this Q point like sort of in the middle of the load line, so that we have enough headroom whenever we will use input signal. Here input signal will vary VGS, right? Because we will apply input signal here, so input signal will vary VGS, and that will basically vary your VDS and IDS. Okay, and we will get amplification. So those amplification part and how it is amplifying, what is the formula of the gain, we will discuss after the puja vacation. So after the puja vacation, we will have we'll find out small signal models of corresponding to this common source amplifier. Okay, small signal models, and we will again find out the gain like we did in case of BJT. We will find out the gain of the MOSFET amplifier. Okay, in that case we will have like GM, we will have R0 and so on. Okay, we will not have RPi. We will not have RPi because you see there is no current flowing through the gate. We will have in the small signal model we will have GM because this is again a constant current source. Okay, you see this is a constant current source, so we will have GM VGS will act as a constant current source. Okay, in the circuit in the small signal model. So in the small signal we will have VGS is open circuit. Okay, because there is nothing here, and there will be a constant current source GM VGS. Okay, and along with R0. So this thing we will discuss in more detail later on after the puja vacation. But I thought I'll just finish it off the DC analysis part today. I'll encourage you to do problems, at least go through the problems present in the Niemann's book as an example. There are several problems considering RS and without RS. Okay, and also the configuration I have discussed, like this particular configuration. There is a important problem they have done in the example, and also they have done problems based on this, which we have carried out in the last class. So I encourage you to do all these problems in the vacation time if possible, because then after the vacation we can straight away start the small signal model of the MOSFET, and we will find out the equation associated with gain and see the effect of RE and all that. Okay, now you have anything to ask regarding this whatever we have discussed in this class today. Then we will discuss about the exam tomorrow. So let's quickly take some questions if you have something to ask very quickly. Please raise your hand. Okay, so if you don't, yeah, please go ahead.
Sir, have you shared the slides of the last class?
Can't remember, I need to check. Probably then if you are saying, then I haven't. One thing I forgot to mention, in case of so usually the enhancement type MOSFET symbol is like this. In case of depletion type MOSFET, we usually make this thicker. Okay, we usually make this thicker to make you understand that that there is a channel already present in the underneath the gate. Okay, so this is depletion type MOS. Okay, and this is enhancement type MOS. Right. Okay.